Okay, so I'm going to start off by looking at a couple of questions, a bunch of questions that came in either people asking me or via the network. Questions are good. Questions, I mean, they keep me honest, they keep me more complete, they remind me things I've forgotten to tell you, and so please, if you can, ask questions. Yeah. We get tired and we stop doing, we stop doing the interaction. So let me start with this one, and I'll display it, and I'm not going to ask you this. Is a question, where is it? What am I looking for? This. Okay. Remember this question from last time? I asked you, I said that if we've got a long, thin bar magnet and I break it in half, what happens to the two ends that are created by the break? Do they attract each other or repel each other? Now, when I asked that question on Monday, I assumed that because the bar magnet was long and thin, that we broke it like this. We snipped the bar magnet like this. So I'm going to come back so you can see me again. And when I do that, if I snip the bar magnet like this tip, which was north to begin with, stays north. This bottom, which was south, stays south. The new pieces become a new north pole on the bottom to pair with the existing south pole, and a new south pole on the top to pair with the existing the north pole. And those two poles, north and south, attract one another. But someone pointed out, what if the bar magnet isn't quite like this? It's more wide and squat, a short guy, and I break it like this. So in effect, it's like if I cut this bar magnet like that, what would the two new parts do? And the answer is the two new parts would still be the portion of North Pole that's now on this half would still be North Pole, and the portion of North Pole on this half would still be North Pole, and those two would repel each other. So if you cut the magnet, if I cut the magnet like this with a saw and had two half magnets, they would not attract each other, no. In fact, what they'll do is one of them will want to flip upside down and stick to the other one. And if you've played with magnets and broken magnets, and I certainly have in the past, that happens. If you break a wide, short magnet, you break it in half, the two halves will still stick to each other, but one of them will be upside down. Is that okay? So how you break it matters, and that's my story. So that was the first observation. Another question. So I've got a bunch of questions, one of which I already talked briefly about last time, or at least I responded to. Do monopoles exist? And the answer from a little bit looking up is, so monopoles, to remind you, would be an object of unknown, the size we don't specify, but an object that has pure North Pole or pure South Pole, just one pole, mono. And no one's ever convincingly observed a monopole. The experiment that took place downstairs from me when I was a graduate student in 1982 was when that happened, is listed as inconclusive. They might have seen a monopole come drifting through their apparatus, but they didn't have enough instrumentation around it to prove it. So it's one of those, well, maybe they saw the only monopole in our galaxy, but we'll never know. The question of whether they do exist or not, according to everyone's authority, Wikipedia, the theoretical physicists are kind of thinking, yes, they probably do exist. We may never see them. We may never be able to create them for various reasons. The process of creating them may take too much energy, if that means anything. So they may have been around during the Big Bang, where there was a lot of energy in a small space. But whether we'll ever see them live and up close is unclear. Anyway, they might, but for all practical purposes, they don't exist. Okay? So that's a first dealing with the question. Second, and a new question came in that I will deal with today for sure. If you isolate an electron, would it have only one pole? And the answer is no. An electron fundamentally has two poles, in effect. Again, no isolated poles are ever seen. So what is an electron's magnetism like? And I left out any discussion on Monday about the, what's an alternative to a monopole, to have a single pole by itself? Well, if you have two poles of equal strength but opposite character, so one's a north pole, one's a south pole, two poles separated by a distance is what's called a dipole, just to give it a name. Makes pretty good sense. There are other poles around. If you have four magnetic poles, a north pole, a south pole, a north pole, it becomes a quadrupole. And physicists and engineers care about this kind of stuff. But that's often the detail land. A dipole is actually important because pretty much that's the basic magnetic thing we've got to work with on Earth, in our universe. The way a dipole works is that if you have two poles of equal strength but opposite character, so you've got a north pole and a south pole, around this magnet, there is not an electric field, but a magnetic field. So what's a magnetic field? A magnetic field is a structure in space that pushes on magnetic pole. And to map out a magnetic field, we kind of pick an imaginary test object that's a pure pole, a pure north pole. Okay, they don't exist, but this is an idea. So you take the idea of a north pole, and you go to every location in space, and you see how is it pushed by the local environment. And if it's pushed, say, upward, then there's a magnetic field where it is, and that magnetic field is pointing upward, and how hard it pushes on my little test north pole tells me how strong the magnetic field is there. So we could, in principle, map out at every location in space the amount and direction of the local magnetic field. So you can visualize this bunch of arrows around this magnet. And that array of arrows in space, and actually not just in this plane, but toward you and away from it, it's a very complicated structure. That arrangement is characteristic of a dipole. If we could have a monopole, it would be a very simple arrangement. If it's a north monopole, the magnetic field would point away from it. Since we can't, we don't have one to work with, the magnetic field around a dipole, two poles, north and south, equal amount, opposite character, it points away from the top, the north pole, and it points toward the south pole because, after all, a little test north pole would love to go towards the south pole. It's attracted. So the magnetic field points toward the south pole and away from the north pole. And it actually is a bunch of, you can visualize a bunch of arrows that fan out from the north pole and unfan, what's unfan? They merge together toward the south pole. So it's a whole structure around, and it has a sort of a looping character to it. Well, that's what you observe around a dipole this large. But what if you start making the dipole smaller and smaller and smaller? And around an electron, there is this same structure. It's pretty wimpy because it's just one little electron making one little magnetic field, but it fans out from the top of the electron. If the electron is spin up, then again, I have still not looked up whether it's fanning out from the top of that spin-up electron and into the bottom of the spin-up electron or the reverse. It doesn't matter. It's one of those things that I look up, okay? Yeah, I'll remember it briefly and then I'll forget it again. I wouldn't trust my memory anyway. So it fans out and goes in. So the electron behaves like it's a little bar magnet with a north pole and a south pole, at least if you explore it out here. Well, if you go in closer, can you get closer and closer? Why would that matter? Because this kind of idea, this idea of a dipole with a north pole on top, a south pole on the bottom, and a separation between the two, leaves something a little uncertain if you go in between the two, like right there. So basically, if I've got a north pole here, a south pole here, what's life like here between the two poles? So for the perfect dipole doesn't have a place to go in between. The way you think of it is you got a north pole and a south pole creating the field. The field out here is quite well defined, but we don't want to, the inside is kind of messy or unclear. So how do you deal with that? Let them get closer together. Now, as they get closer together, the two poles, imagine you've got North Pole and South Pole, bring them to half their original separation. As you do that, because they're closer together, they influence our little test magnetic pole more evenly. When they were widely separated, the north one up here where my finger is waving was significantly closer to this little test guy, and it dominated the influence. This guy over here is a minor player. But as I bring them closer, they're acting kind of equally, and so the magnetic field gets smaller. So the distance of the separation matters. As the two poles get closer and closer, the strength of the magnetic field shrinks, because they're kind of, the two are more and more canceling each other. So how do you compensate to have this sort of the same oomph, to have the same field out far away? Well, use bigger poles. So as you bring the north and south pole closer together in this little dipole I'm waving my hands about, so you bring them closer, you also have to boost their strength. So what really matters is the amount of pole and how far they're separated from each other. If you shrink the separation, you have to increase the amount of pole. And you can just take that to the limit of no separation. So they're infinitesimally close to each other, but very strong. And that's kind of the field that lives around an electron, is the magnetic field of two very closely spaced poles, as close as you like, so close you can't see between them. But they're very strong, and so together they produce an electric field anyway. So that's the field around most subatomic particles, actually. So electrons, it's true. Electrons, it's true of most of the, neutrons, protons. I think they all have magnetic character to them. The electron's the strongest of the bunch. And even if you start going under the hood and looking within neutrons and protons, because they're made up of stuff too, the famous quarks, they're magnetic too. I mean, everybody's got, magnetic dipoles are just all over the place. So I think I've said everything correctly. I'm suddenly a little anxious about, it's an electric dipole moment that people have been looking for in the neutron. The neutron, I think, actually has a magnetic dipole. There's some of this stuff I don't pay attention to since like graduate school, and it's kind of evaporated. Okay, so the electrons, the materials that we deal with in everyday life, what we're made of, the chemicals we're made of, the materials we're made of, the stuff around us, the metals, the insulators, the water, all, if it's anything that exhibits magnetism, it's because it's got electrons in it, and because the electrons are exhibiting their magnetism. There may be a few bizarro exceptions, but that's pretty much the story. And I went on a long-winded story last time about the cancellation effects that occur, that wipe out magnetism in almost everything with rare exception. And one of the rare exceptions is iron, and I'll come back to iron in a minute. I did make the incorrect claim that iron had, I thought, 16 electrons. Now it's got 26. I should know better, but tough to remember. Before I go back into how iron's microscopic magnetism is something we observe all the time, let me pick off the rest of these questions. So electrons, definitely, they're a magnetic dipole. They have they have the magnetic field of a north pole and a south pole that are very close together. There's a question about graphene and the magnetism, the electrons moving in graphene, which is a little bit of a side issue, but something that I did leave leave behind. I told you that for charges to move through a material as an electric current, you got to push, right? Even copper and silver, both of which are really very, very good electrical conductors. If you want a current of electrons to flow continuously through a chunk of copper or a chunk of silver, if you've got lots of money, you need to push with an electric field. How do you make an electric field in this material? You expose the material to a difference in voltage. So it's got a higher voltage at the entrance and lower voltage at the exit. There's now a voltage gradient from high to low in the material, which is an electric field, which pushes charge. And so charge works its way through the material as an electric current. If you have the same voltage at both ends, also from the problems that refer to as the same potential at both ends, no current flows. All right? So that's the nature of basically all our conductors and so on. We'll come back to the fact that if you want more current to flow, you push harder, you use a bigger voltage difference, which I mentioned is Ohm's law, that the current flowing through the material is proportional to how hard you push. In other words, how big the voltage difference is. That said, all around, there are some weird materials that sort of violate some of these rules. Graphene, which is it's a two-dimensional sheet of carbon atoms. It's basically graphite, ordinary graphite, but just one layer of ordinary graphite. And graphite, like mica, if you ever peeled apart mica, it's little layers, and you can peel it apart. You can peel apart graphite the same way, until finally you've got just one atomic layer thick. And that's been a big deal for the past, I don't know, 20 years. Graphene has been like a hot topic. Anyway, it has very good electrical conductivity along its plane. It conducts, some whopping value bigger than silver and stuff. So, but I think it still wants, you still got to push. You can get the charges to enter one side of one of these little sheets, and it won't quite coast to the other end. So it has interesting properties in its conductivity, but it's not really just completely out of the picture here. There is something that's out of the picture here, and that is materials known as superconductors. And you probably heard that term before. What a superconductor is an electrical conductor that truly does not require any push to keep the charges moving in it. The charges move in it inertially. If you get them started moving, they will continue moving for free. So it's everything I said about conductors always charging, that's with the exception of superconductors. The reason superconductors manage to carry current absolutely perfectly without taking any energy out of it is because of quantum mechanical effects that forbid the moving charges from essentially hitting things. They cannot stop and hit because quantum mechanics forbids it, special cases. And as a result, you can get them started moving and they'll keep moving. Really, essentially forever. As far as we know, they just keep, there are reasons why they will slow down by dissipating energy in interesting ways, but that's in certain types of superconductors. The classic superconductors cannot even use that mechanism for dissipating energy. Once you get the charges moving, they move forever. You can put them in and they'll keep going. And those superconductors typically they operate at low temperature in order to get the quantum mechanical effects to be important and trigger this transition to superconducting. You got to go very cold. The original superconductor, I think, was mercury, liquid mercury, which if you cool it becomes solid mercury. And if you cool it enough, oddly, it loses its electrical resistance. And I think this was Camerling Onus, the same person who figured out how to liquefy helium. So we're at liquid helium temperatures, which is a couple of degrees above absolute zero by any temperature scale you like. So it's really cold, and mercury lost its electrical resistance, which was just like a shockaroo, one of those jaw-dropping moments when something weird is happening. And yeah, something weird. We encounter superconductors now primarily in things like big magnets, and we haven't yet gotten to why big magnets and superconductors would have anything to do with each other, but we will essentially get there. Anyway, so if you go for an MRI, in a lot of cases, magnetic resonance imaging thing, part of what they do is they put you in a very strong magnetic field, the same magnetic field we've been talking about. And how do they make that magnetic field? They do it with superconductors, and we'll see that electric currents are magnetic. I mean, to give away spoiler alert, electric currents are magnetic. And as a result, they can make very strong magnets with very large electric currents. Well, keeping large electric currents going in ordinary conductors is expensive because you got to push. You need voltage drops. But in superconductors, you don't. You can get the current going and it will keep going forever. And as a result, there are situations where you can purchase a superconducting magnet with the current already going as introduced by the company. The company gets the current going, packages it up, and ships it to you. And it arrives with current going. And it never stops until you stop purchasing a cooling agent and it overheats. Actually, one of the masters of superconducting magnets is Al Tobias, the lecture demo guy here. He is sort of one of the local experts in superconducting magnets, which exist in this building, or at least on grounds here, in various contexts. Okay, so I'll probably drag out some superconductors at some point. We can play with them. There was a very important discovery made, I don't know, 30 years ago about prior to a certain point, you couldn't make superconducting magnets without liquid helium around, which is a pain in the neck to work with. I know at one point in my undergraduate career, I worked with it. It's expensive and complicated and very cold, okay? But about 30 years ago, people discovered what are so-called high-temperature superconductors that become superconducting at liquid nitrogen temperature, which is cold, but you can deal with it. And so we can play with those at some point. I'll drag them out. So bottom line is there are conductors that do not require electric fields to keep the charge moving. We rarely encounter them. There is a small chance that people will manage to get this behavior to go all the way to room temperature, in which case it may become an important part of your lives. Electric power distributed using superconductors would be great, because as I told you at one point, the national and international power grids waste a significant fraction of their energy pushing the current through the wires and making electric heat by accident. So with superconductors, that would not happen. And so it's a possibility that will show up in your lifetimes as a way in which to distribute power. Okay, more questions here. How does magnetizing other metals work? So I have to talk about magnetic structure and stuff of materials, something I sort of started on last time but didn't do a good job with. And associated with that, the question about how does a strong magnet change the poles of a weaker magnet? Also something, the same topic, and I have to talk about it. And how does potential energy affect magnetic systems? In general, magnets, like everything else, they accelerate in the direction that reduces their total potential energy as quickly as possible. So if I have two magnets, for example, here, two magnets, and I guess that the reds are north poles and the south poles. If I take these two north poles, they hate each other, right? If I push them together, I am doing work storing energy in their magnetic repulsion forces, and see it's stuck north to south, south to north. Didn't take my fingers with it. Anyway, it tries to get rid of potential energy. It has done that now by bringing opposite poles close together, an activity that involved doing some work on me, fortunately not on my fingers. So basically, whenever you create poles, a significant dipole, for example, big north pole here, south pole there, it's as though you started with north pole and south pole overlapping, and you pulled them apart, an activity that requires work. So magnets, particularly these permanent magnets, have a lot of stored energy, and they would love to get rid of it. Trapping that stored energy is a challenge, and that's part of modern magnetic materials. All right? So where I'm going with these questions and what I needed to deal with now is to tell you, so how do you make a magnet, a permanent magnet, one that remembers that it's magnetic? And what's the alternative, like ones that don't remember they're magnetic? Okay, I told you that electrons are really underlying all these magnetic materials, and in most cases when you assemble something big enough to see, all the electronic magnetism is canceled. You have, in effect, paired up electrons. For every electron that has a north pole on up and south pole down, you have an electron that's the reverse. They coincide adequately enough that they kill off each other's magnetic fields. So there's just nothing. So people are we're pretty much non-magnetic. No magnetic field around us or in us. And most materials are like that. Copper, same thing. So I'll go back to sort of what I was doing last time. So copper, it's almost perfectly non-magnetic. There's nothing left in this thing. I got to be careful not to move it. Motion is we'll see motion's important, has weird effects. If I do begin to move it, yeah, okay, no, I'll set that aside. We'll eventually deal with motion. But if I hold copper up to the swivelly magnet doesn't pay any attention. There's just nothing magnetic in copper, to the point where for some laboratories where they wanted to be very, very sure there was nothing magnetic around, they actually used things like copper nails as opposed to steel nails. Bad idea. Steel is magnetic. Copper, not so much. Same with aluminum. No magnetism. Steel, different. Steel's magnetic. Okay, so what's magnetic about steel? If you look at a big chunk of steel just right out of the factory, it will exhibit no obvious magnetism. Take two chunks of steel, put them nearby, they don't care about each other. So the default state of steel and iron is exhibiting no magnetism that you notice in the real world's environment. So you can go to an appliance showroom and the appliances are not leaping at each other because of magnetic forces. But if you zoom in at steel, magnify it many, many times, you discover, it has little patches, and I mentioned these last time, called domains. They're called magnetic domains. And within a single domain, it's not, to recognize the domain, you can't look for the atoms. The atoms look normal. You can't see the boundary between two magnetic domains. You have to look magnetically, and you discover, this region of atoms, this patch, has locally magnetic, and they're all oriented the same way, so there's like a North Pole here and a South Pole there. And you look at another domain, and it's also locally, everybody's lined up. They're all the little the atoms are magnetic, and they're all agreeing to point North Pole here, South Pole there. And they end up looking like, and we're going to look down at this array of little compasses, little compass needles, which are in fact magnetic. So we're going to look down on that from above with a document camera on this. There we go. And I'm going to dim the lights a little. So the one I want you to look at is this guy. If you look there, you will see that those little compass needles are aligned with each other in patches. There are a couple compass needle arrows that are confused and are pointing backwards, which is itself an interesting observation. When this was built, they all had North Pole at their arrow point and South Pole at their tail. Some of them have been confused and flipped, and we'll come to how that happens. But the main thing here is you see, with a dangly thing in the way, but that's okay. I can shift this over a little so there's nothing. Then I get reflections. I'm going to leave it like this. Okay, so you can see the patchwork assembly of the magnetic orientations. There are some domains, like here's one here that I sort of circle around it, that is everybody's agreeing. But adjacent to it is another patch that everyone agrees differently. And this one, this patch here, you all can see the domains? That is the way normal steel is structured magnetically. It contains these little patches that agree, but adjacent to them are patches that don't agree. If they were to all agree, there's a lot of energy stored in that, because now you've created a large magnetic dipole. All the North Poles are on one side, all the South Poles on the other. You've, in effect, pulled apart as North Pole and South Pole, an activity that requires a lot of energy. The system doesn't like that. It tries to get rid of that extra energy. And it does that by flipping some of the domains backwards. In much the same way that, here I had these two magnets, and I was playing around with them a little casually, forgetting how fiercely they attract each other. If I try to bring the two South Poles together and North Poles together, it doesn't like this. It wants to flip them upside down and put one, so that one of these magnets is North Pole up, the other one is now North Pole down. It likes that. That releases energy. And the same thing happens with domains. If you've got two big sort of identifiable regions which are both North Pole up, they hate that. They would like to flip one upside down. Okay? So this is the domain structure that you find by accident just looking in steel. Can you change that? And the answer is yes, you can. If you bring a strong magnetic pole, and what I'm going to do is I'm going to bring a strong North Pole up to this lattice of little compasses, and it will sort of dominate the effects, at least locally. The domains will start shifting. And here we go. You can sort of see them change their mind and line up. And now, most of it is all lined up. I've changed the domain structure. And the way this happens in real life in a piece of iron or steel is the domain, the edge between two domains begins to move across the material. So that the domain that's lined up correctly with the strong external magnet grows. The edge begins to swallow up all the domains that are pointing the wrong way. And so they all line up together. So what I just did was, in effect, I magnetized a piece of iron or steel, and it's a piece of steel that is capable of staying magnetized. I told you that there is that demagnetizing effect of having a lot of them lined up, is a lot of stored energy. They kind of want to undo this, but these guys aren't able to do that. If I do want to get them to unline up, I have to actively demagnetize them. And the way I do that is by bringing a pole up and jiggling it around, or subjecting that to sort of a mixed variety pack of magnetizations, like this. I get them all confused, and now they go back to their domain structure, the normal domain structure. So magnetizing means bringing up a strong pole. Demagnetizing, sometimes it happens spontaneously because of thermal energy. Sometimes you have to do it actively by bringing up some crazy mixed up pole. And I don't know whether you guys basically have ever seen an old color tube TV. Remember color TVs that weren't flat panels, that actually had a big box and what's called a cathode ray tube in them? Color television sets of that era had a magnetizable but not magnetized shadow mask just inside the colored screen that helped in the mechanism for creating the colors. And so inside that plane of glass of an old television set was a magnetizable piece of metal with tiny holes in it, beautifully made, structured system. It had to be magnetic for complicated reasons. And when we first got our color television set, the first one in 1965, I had a very strong magnet. Up until that time, with our black and white television sets, I had been making curveballs on the TV. In the view of, I know this is a completely aside, but magnets affect moving electric charge, just as moving electric charge affects magnets. We'll get there. And so I could move the electron beam that was drawing a baseball, moving from the pitcher at the top to the batter at the bottom in a particular view that was at least popular back then for baseball. And I could make it so the ball would go woo out to the side and then get to the pitcher with my very strong magnet. That was fine with a black and white television set that did not have a shadow mask in it. It was not so good for a color television set that did. And so I promptly magnetized our television set, and all the colors were just whack-a-doodle for several days until we had the repairman come and demagnetize the set. So I basically did this to our set, and it stayed that way. And the demagnetizing guy came up, and I fortunately didn't get in trouble, but I didn't tell the entire truth to the repairman. All right, back to business as usual. So you can see with magnetic materials have this magnetic domain structure. This is completely absent in copper, aluminum, wood, plastics, most things. It's present in steel and a few other things. Steel, iron, and a few other things. Very rare. Philip?
If you cut out the domain, would it retain its qualities?
If you cut out the domain, would it retain its qualities? The answer is yes. And oddly enough, one incarnation of my research was tiny pieces of iron and other elements. How magnetic are they? Tiny pieces being 20 atoms, 100 atoms. So downstairs, we actually studied iron particles that were dozens of atoms large. And it turns out they're extremely magnetic. They're more magnetic than bulk iron because they're almost all surface. And for reasons, the surface is important. So yeah, they are magnetic. Actually, they are single domain. The energy cost of introducing a domain boundary is too much. All right? So pure iron spontaneously demagnetizes when you take away the magnet. So you can align them in pure iron, and when you take away the magnet, thermal energy alone at room temperature manages to flip some of the domains and reintroduce domains the other way, and it forgets its magnetism. So pure iron, that's useful for some stuff, like pure iron and some of the softer steels, I guess, would qualify too. They don't remember magnetization much, which is good for your refrigerator. You don't actually want to magnetize your refrigerator and have it stay that way. You want to bring up, and I should say, why does a refrigerator magnet stick to a chunk of iron or your refrigerator? It's because when you bring up the magnet, it lines up the domains in your refrigerator. And they line up in such a way that they attract the approaching pole. It's all good. You're polarizing the refrigerator and then sticking to it magnetically. And when you take away the refrigerator magnet, the refrigerator goes back the way it was pretty much. It's not magnetized permanently or barely. Yeah. There are other materials, though, that are somewhat sort of engineered so they don't demagnetize spontaneously. They keep it. And the permanent magnets that you're used to seeing, and the refrigerator magnets themselves, are of that type of material. The distinction between these two types of material, pure iron is a soft magnetic material, meaning you can magnetize it, but then it forgets. The permanent magnets are hard magnetic materials, meaning you magnetize them and they remember. And the past 50 years, people have really improved the capacity of hard magnetic materials to remember magnetization. So they're now really good. And yeah, I mean, the magnet that I was playing with on my television set was nothing compared to these guys are way stronger. The magnet I had back then was as good as you could get for back then, but this is much better. So these are hard magnetic materials. Hard magnetic materials typically have internal structure that, among other things, makes them physically hard and brittle. So some of the best magnets are also fairly fragile. Pure iron is actually pretty soft. You'd have a tough time breaking pure iron. You could pound it into a puddle. You can work it like a blacksmith. It won't shatter, or not easily. Whereas like these magnets, you hit them with a hammer, they will not. They won't yield. They won't spread out. They'll just break. Okay. So having said that, these magnets were made of a material that's magnetizable. That is, you can magnetize it and it will stay magnetized, a hard magnetic material. And then they were magnetized. When they first came out of the assembly line, they weren't magnetized. They had no North Pole and South Pole. Somebody had to teach them the North Pole and South Pole, and that was basically a strong magnet. And it is possible to magnetize them correctly or incorrectly. So these guys are magnetized correctly. That's actually a south. This is a North Pole. It's North Pole, North Pole. Everybody agrees here, right? But I can go in here and I can put the North Pole and the South Pole generator. This device creates a strong magnetic field. Where's that iron? This is the iron. Yeah. So I'm going to magnetize them wrong. Boom. It happens to use electricity to do this, but there, I did it twice. Okay. So this is a North Pole again, right? Whoa, no. This guy's, he's messed up, man. The end that's labeled north is now a South Pole. You all see how that's the case? So you can magnetize it the wrong way, and some of the arrows over there have been that way. So we've screwed this guy up. So now I can get it back to normal. Okay. Up. We fixed him. Okay? So as an observation then, hard magnetic materials are great. They can be magnetized, but you have to do it. And so you have to do it right. If you do it wrong, you get them backwards. It's okay, I mean, it just happens. But you can do interesting things using that ability to magnetize and stay magnetized. And this has to do with magnetic memory. What do I want to do next? What I want to show you is magnetic memory. Hard drives still exist, right? They haven't quite gone away. People are getting solid state drives, but some fair fraction of you in this room have hard disks on your computers, and they are storing information. Where? They're storing it on a surface of hard magnetic material by magnetizing little patches of that very strategically. They magnetize the North Pole one way or South Pole one way, and they do it strategically to create patterns that represent information. And we can see patterns like that, things, too many random things to do. Your hard drives do this. Back in the day when tape recorders were still around, and there was an era when I taught how tape recorders work, the magnetic tape, which still at least has some cultural resonance to it, it has little patches of hard magnetic material on them. You could magnetize them one way or the other way. And the tape recording process involved magnetizing these little areas, such that they would represent sound, for example. Advertising, the advertisements that you stick on your refrigerator that you get from the pizza place or whatever, they are hard magnetic material too. There happens to be a pretty flexible sheet of hard magnetic material. It's a mixture of plastic and hard magnetic material together, so it's sort of kind of flexible. And they are magnetized with poles. And the poles are distributed in an interesting way. With that in mind, actually, I should show you the poles around an ordinary dipole. So here's an ordinary dipole. And we're going to look down from above at this magnet. And I'm going to put the magnet underneath the paper so I don't get powder on it, and I'm going to sprinkle iron powder around it. And the iron powder, because it's easily magnetized, it's not magnetic, but it's magnetizable, it gets polarized, it fleshes out the magnetic field. You sort of see streaks. You can't tell whether the magnetic field's going away from the North Pole or toward it, but it's going away, I promise you. It swoops around and goes toward the South Pole. In the middle, where life is complicated in a physical dipole, it's messy. In like the electron dipole, there's no middle. But so there you get to see. The point here is that yes, there is this interestingly structured magnetic field around a magnetic dipole, and the material does leave the North Pole and go toward the South Pole, and it particularly loves to be on the poles themselves because that's where the magnetic field's strongest. And they get sucked in there really quite strongly. They polarize and get stuck, just like magnets stick to your refrigerator. Okay? So we've seen that. So let me get that away, and let me put down a more complicated magnet, namely one of these guys. So it's a refrigerator magnet. I'll put that under and cover it over so I don't have to clean it, and sprinkle I shouldn't have touched it, make a mess. I need the sprinkling effect. You can see it. I can probably make it clearer by zooming. I'm going to zoom in. What I want you to look for is horizontal stripes. And zoom in, zoom. Do you see that there's a horizontal stripe character to the pattern? It's poles. North pole is a stripe, south pole is a stripe. North pole is a stripe. These magnets have lots of poles, not just two. It's not a dipole. It is a whole series of poles. Can I make them? This is helping a little. You can see the horizontal stripe aspect to it. It's got many poles on it, and in this case, no information. It's just they got a whole stripe of North Pole, a whole stripe of South Pole, a whole stripe of North Pole, and when you put it on your magnet, it locally magnetizes the iron sticks. That's all good. The magnetic field has this funny structure where it points away from the North Poles towards the South Poles, and then away from another North Pole towards the South Pole, and so on. Credit cards. So where I'm going with this, credit cards with magnetic stripes are starting to disappear too, which is like okay, well, are you going to leave nothing left for me to talk about? Probably. But if I take a credit card, I don't want to do this. If I take, I've done it before, and then I got to clean my credit card off. If you take a credit card and sprinkle it on, you get the same kind of thing, except first of all, it's smaller. The pattern is very small. Just little North Pole, South Pole, North Pole, South Pole. And it's erratic. Where the North Poles are and the South Poles are isn't uniformly spaced. It's encoding information. And so when they write your credit card, they're putting the poles in by magnetizing it. It's a hard magnetic material. It remembers the magnetization. And the pattern of the poles represents your name, your credit card number, and so on. And those of you who had credit cards that sort of lost their memory because you did put them near something, they got exposed to a strong magnetic field somewhere, and it wiped out the magnetization. It changed them. It's like this guy reversing the poles. All right? So let me come back out of this. I got one more thing to do before finishing. So we've seen permanent magnets. Is that all there is? Is the only way you can make a magnetic field with a permanent magnet and the electrons that just come with it? And the answer is no. And to illustrate that, what I've got here is an electromagnet. It is iron. There's iron here, big chunks of iron. But it's really iron. It's soft magnetic material, no magnetization that you can see. They don't stick to each other. They don't care about each other. Who cares, okay? But we can line up the domains in there one of two ways. I can bring up a strong permanent magnet and get them to line up. And the permanent magnets will stick to this. I mean, it's not interesting, but the other thing is I can expose it to another magnetic influence that will line up the domains. And the other influence is moving electric charge. And Ørsted first discovered moving electric charge is magnetic during a lecture in 1820. He was giving a lecture, and he noticed that when he ran electric current through a wire, a compass needle nearby moved. And up until that point, there was no evidence that magnetism and electricity had anything to do with each other, but they do. So I'm going to move an electric current through wires. They happen to be wires wrapped around the iron, and it will line up the domains in the iron. Okay, it's flowing, and this, basically, I defy anybody to pull that piece of iron off. It is stuck so hard, you can't do it. And, where was the magnetic influence that did this? It's the current. If I turn off the current, and as I do that, there's a lot of energy stored here because we separated poles, right? When I open this circuit, watch what happens at the switch. No sticky, it turned off. Current on, stick like crazy. Actually, even worse if I go from North Pole to South Pole. This is forever, okay? So, last version of this, I might as well do because he keeps setting it up. Sorry, I know I'm getting very late here. Is this one. Same idea, iron, non-magnetic by itself, But if we switch on the switch, right? Okay, turn off the switch. It takes a little while for this guy to forget. I think I've done it. There it goes. Okay, so electric currents are magnetic, and that's this part. You guys can come play with this. That guy you can play with too. Don't touch any wires, and don't get your hand between the iron and the magnet. It will smash you. All right.